Many of you have requested in the comments under my previous videos that I present more of the milling machine that has occasionally been shown here. Well, your wish is my command. In this video, I will feature my DIY Epoxy Granite CNC Router that I have built a few years ago. The reasoning behind the material and design choices, the specs, the mold making and casting, and some footage showcasing its performance. And if you're interested in a sneak preview of my upcoming projects in 2026, watch till the end. Hello and welcome to my channel. My main CNC machine is a DIY router with an epoxy granite base, which I built in 2023. It is a desktop machine and I explain later why. The design principle is a heavy C-shaped base with a cutout in front to allow some vertical clamping. It has left and right two massive risers milled out of a solid piece of aluminum. On these risers rides the gantry, which is built around a massive 200 by 100 mm extrusion, filled as well with epoxy granite. Since the router had to be wider than deep, this design proved to be very rigid, with minimal lateral deflections and overall vibrations, even when I pushed the spindle to its limits. The work area is 1050 by 760 by 230 mm, with a table size of 1050 by 610. I can place two large 500 by 500 mm vacuum tables, a couple of vices, or a mixture of both on the table. In the vertical clamping fixture, I can work on parts up to 940 by 100 mm with a max height of 340. The overall weight of the router is around 700 kilo and the footprint is 1900 by 1140 with the base plate being 1600 mm wide. The axes are driven by a 400 watt delta servo on X, two 750 watt servos on Y, and a 200 watt servo with brake on Z. The spindle is a water-cooled Spinogy X30 with a 4 kW 4-pole motor, 30k RPM and a SK30 ATC interface. A few years ago I built a CNC router out of ultra-high performance concrete, UHPC, and this was really a beast in terms of rigidity. It performed really well, but when my interest moved away from scale modeling to building CNC routers, I soon realized that the work area of 600 by 400 mm was too small. So I made the decision to build a larger machine. Unfortunately, this meant that I had to completely rebuild my workshop to create the necessary space. On the other side, it was a good opportunity to rearrange a few things based on the experiences made working for a couple of years in the original layout. But as you can imagine, and as we'll see, those were days of complete chaos because I had no room to place everything and I was obliged to store all the drawers and cabinets in the middle of the shop and to somehow work my way around them. In this process, I sold the UHPC mill and it required a company specialized in moving safes and pianos to get the 400 kilo beast in one piece out of my basement. I also sold my welding table, which was no big sacrifice, because apart from the table itself, I never really welded much anyways. A key requirement was that I could reuse the control cabinet of the UHPC mill together with the new larger router. Fortunately, this was relatively easy to achieve because it just moved from one corner to the other and switched places with my woodworking router. Once the new layout was done and everything was back in order, I started with the mold. At this stage, it was in fact the last part to make because I already milled all the other parts for the new machine on the UHPC before it was sold. The mold was made out of 25 mm thick MDF board. Since I couldn't mill a 1600 by 1140 mm large plate, I built the mold out of 3 plates which I connected with lots of 75 mm wide MDF strips. Both the plates and the strips I could easily drill in 2 setups on my woodworking router in order to get the correct spacing of the countersunk holes. You may have noticed that I have not properly recorded the build of this router like on my latest machine because at that time this channel simply didn't exist yet. Still, if you like the video so far, please give it a thumbs up. And when you don't want to miss my next CNC router projects, which I will talk about at the end of this video, subscribe to the channel and hit the notification bell. The assembly was done right on the bench where the mill will finally be placed. It is not really important that the surface you build on is not dead flat like a granite control plate, for example, because you never achieve a dead flat part in the DIY setup anyway. But that's no big issue, and I show you later how to deal with this. I ordered some 1.5mm thick aluminum plates at a laser cutting service to line the inside of the mold. This has several benefits. First of all, this guarantees a perfect alignment of the 8mm holes for the threaded inserts across the entire mold. Secondly, I do not have to apply any release agent at all to prevent the MDF and the epoxy to form an eternal bond. And lastly, I don't have to seal the epoxy granite later on to withstand the cooling fluid. My experience with an epoxy coating on the UHPC mill was not so great. I also ordered the threaded inserts from a machining shop, simply because I was too lazy to turn some 150 inserts by hand on my manual lathe. They are made out of 7075 aluminum and are fixed to the mold from the bottom side. That's why I milled the countersunk holes in the MDF earlier. I also added some ports and tubes for the vacuum. The integration of such a feature is one of the many benefits of epoxy granite or concrete machine parts. Before I started to mold, I made a few test parts with different ratios of aggregates and epoxy. Epoxy granite mixes are not so well documented and the stuff is rather expensive, so the aim is to use as little resin as possible. Industrial mixes have less than 10%, but that was too brittle in my case. I measured the deflection of the parts under a given load and made as well some destructive tests to check the grain structure. I settled in the end for a 12.5% epoxy content with an aggregate mix based on a Fuller curve. The reason I went this time with epoxy granite and not UHPC is simple: logistics. UHPC is cheaper than epoxy granite, but it requires a drum mixer. In contrast to epoxy granite, you cannot mix it by hand in a bucket, and it takes roughly 30 minutes of mixing until it has the correct consistency. A plate of that size and weight is impossible to carry downstairs in my basement, so the casting had to be done directly in the shop. So I prepared 12 buckets with 20 kilos of the correct mix of the aggregates. Then I mixed 12 times the correct amount of epoxy, mixed it with the aggregates and poured it into the mold. I used an epoxy with 210 minutes pot life, and believe it or not, the entire casting process took me exactly 3.5 hours. So the first pour started to cure right when the last one went in, which gave me a fairly homogeneous curing throughout the part. In between the pours, I compacted the mix with a hammer. There is absolutely no point in trying to shake a mix dry like that, besides I don't have a shaker that size. After half of the curing time, I sealed the surface with epoxy and leveled it in a second step, again with epoxy and gravity. Finally, I epoxied another 1.5mm thick alu plate on top to minimize any later on bending due to an uncompleted sandwich. And with this, the casting was done. After a few days, I flipped the mold onto my mobile workbench and pushed the casting in place where it was demolded, piece by piece. The plate rests on a 4mm thick EPDM foam, which evens out any irregularities in the surface between the bench and the plate. The next task was to create an even plane for the y-axis. I used the long straight edge and the machinist spirit level for this, and added gauge blocks front and back under the two risers left and right until I achieved the desired result. Then I milled 4 spacers with the correct height, placed them where the gauge blocks were, and applied a leveling mass. I used Wycon F for that, which is specifically made for this purpose and for alu-to-alu surfaces. After 1 day, the stuff was cured and I bolted the risers to the base plate. Then I added the gantry and started to align everything to be mechanically as square as possible. The fine-tuning is done later with the software gantry squaring. The first manual movements were quite satisfying. The 200 by 100mm extruded aluminum profile is filled with epoxy granite in order to minimize vibrations. I added 2 risers for the linear rails, and the exact mounting surface was faced by a friend of mine who is a professional CNC machinist. He was also so kind to mill the 2 gantry risers out of a massive aluminum bar. The material is sawn out of a casted plate and already has very minimal internal stress. Nevertheless, he did it in several stages to guarantee that there is no distortion in the parts despite the huge material removal. A true expert. The 30mm thick gantry side plates and all of the Z-axis parts were already made earlier by myself while the UHPC mill was still up and running. The CNC controller is split into separate boards. A high voltage board with the VFDs for the spindle and the vacuum pump and the servo drivers. And a low voltage board for the aiding CNC control board and its peripherals. At this stage I already tuned the tandem Y-axis servos. I did that with one servo decoupled and without the Z-axis on the gantry. This represents roughly 60% of the final gantry weight and is a good value for the auto-tuning. The delta servos have a true auto-tuning feature that measures the real inertia to load ratio and sets the parameters accordingly. This makes the tuning process really simple. As always, you have to fine-tune the position following error, but that is really all there is. I have almost no video footage of me completing the router with the Z-axis, but it is quite comparable to the one I used on my latest build. So when you want to learn more about it and haven't seen the video yet, I'll link it in the description below. With the machine completed and fully tuned, I finished the enclosure. The benefit of placing it in a niche was that I just had to do the front with the controller compartment on the right and the sliding door on the left. I prefer these large sliding doors over swing doors because you still have full access to the touch screen and the controls when the door is open. The enclosure not only prevents me from being shot blasted with chips, it also dampens the noise quite effectively. Then I set the number of steps per millimeter in the control software and verified with a glass scale that the positioning command of 1000 millimeters is in fact 1000 and not something else. And of course the same process was repeated on the Y-axis. With the correct distance set, it was time to complete the machine with the fixture plates. At first I glued a thin acetal sheet to the front where the vertical fixture plate will go and made sure this is perfectly perpendicular to the Z-axis. And then the same with a thin alu plate on top of the base plate. This way I avoid to put any stress in the 30mm thick fixture plate. The fixture plate itself is made out of a cast 7022 aluminium plate, which has a rather high surface hardness and yield strength for aluminium. This makes it easy to machine but yet durable. I first drilled and milled all the countersunk holes for the M8 fixation bolts, which are arranged in a 100 by 100 mm pattern. With the large fixture plate roughly in place, I started the vertical fixture. This goes into the C-shaped cutout in front of the base plate and is bolted to the epoxy granite base and the fixture plate. There is a fixed jaw and a moving jaw attached to the vertical fixture, which slides in two T-slots across the full length. Both plates are then bolted together and to the epoxy granite base in their final location. I also turned some aluminum caps that are pressed into the countersunk holes to close them. What's left is to drill and tap the thread pattern. I first started with the M12 threads for the vices and the 15.9mm holes for their 5/8 location pins. They are fixed with an O-ring in the vise, and this makes it really easy to repeatedly place the vise correctly aligned on the table. I have about a dozen of these spaced out across the table, which gives me a really flexible setup. The fixture plate has a 50x50mm grid pattern of M8 threads combined with an 8H7 hole on top for dowel pins. I had this system on several mills so far, and it proved to be really versatile. I first drilled the 6.8mm holes about 28mm deep. Then I drill into the same holes with an 8mm drill about 7mm deep. This gives a rather good tolerance for the dowel pins. And lastly, I mill the M8 threads from -27 to -7mm. And finally, the entire plate is faced with an 8mm end mill and a 60% step over, only with a climb cut. This takes forever, but it is a once in a lifetime job, and the reward is a perfectly flat fixture plate. The vertical fixture is a real game changer when it comes to adding threads or other features into the sides of parts that are too tall for the vise. The loose jaw is first placed against the side of the part and fixed to the plate with M6 bolts. Then the part is clamped with two cam screws from Kip. I changed the M6 bolts later to a flat socket head cap, so now I need only one Allen key, which makes things a little bit easier. So, this is it. I do have to say that after more than 1 year of usage, I'm really happy with the performance of the mill. The only issue I have is the chip management because of the desktop setup. Chips pile up quickly and I have to remove them after a few jobs by hand. The desktop setup was necessary because in the limited space of my workshop, I need the area below the mill to store all the end mills, tools, measurement equipment, and so on. I hope this little recap of the build met the expectation of you guys who have requested it. Again, I have to apologize for the poor video quality, but most of the pictures and videos were shot for a different media well before this channel existed. So, what's next? As promised, here is a sneak preview of the upcoming content. If you don't want to miss it, please make sure you subscribe to the channel and hit the notification bell. Early 2026, I will start a custom order of a complete CNC machine based on my Watchmaker 5040 design. It will come with a full enclosure, control cabinets, spindle, vacuum table and pump, the full lot. I'm really stoked about that. But the big news is that right after that, I will move my activities out of the basement and into a proper shop. I have the opportunity to get a free space in a workshop, which, as you can see, is still used for other things today. I will show here how to turn that space into a semi-professional work area. And of course, I need a new mill for that. Both of my existing machines are too big and heavy to ever leave my basement again, and I might as well work in parallel. Smaller parts at home, big and heavy parts, and as well assembly in the shop. I don't want to disclose too much about it yet, but what I can say, it will be a UHPC machine again. Let me know in the comments below what you think about this development. Stay tuned and see you next.